Good morning. So now we will now begin our supplementary discussion on some of the parts that need to be computed in terms of FM and PM. So we will begin with the discussion on how we are able to actually determine FM's frequency deviation, modulation index, and bandwidth. So from our previous discussion, FM or FM's frequency deviation is the largest amount of change in the frequency of the carrier signal as compared to the amplitude of the modulating signal. So frequency deviation can be expressed as F sub D, or in this case, this Greek letter here. There are cases that frequency deviation is actually given in a problem, but it is actually a function of the deviation sensitivity of the FM modulator given in rads per second volt or rads per second volt, and the peak modulating signal amplitude. So the peak modulating signal amplitude is given as that is the highest amplitude of the modulating signal that would actually result into the highest frequency deviation. So let's take a look at some sample problems we could use in order to determine frequency deviation given the deviation sensitivity, which is K2, and the peak modulating signal amplitude, which is V sub n. So for this example, we have a worded problem that is asking us for the peak frequency deviation for a FM modulator with a deviation sensitivity of 10 kilohertz per volt and a peak modulating signal of 5 volts. So for these types of problems, it's actually quite straightforward, as we just have to multiply our deviation sensitivity, and you'll notice that with the kilohertz per volt, or in some cases rads per second times volt, and of course the peak modulating signal amplitude, which is 5 volts. So let's take a look at how we would be able to determine the peak frequency deviation. So from our formula, we have our delta here, and we just have to multiply K2 multiplied by V sub M. So again, K2 is a frequency deviation, which in here is mentioned to be 10 kilohertz per volt. And then we just have to multiply it with a peak modulating signal of 5 volts. So multiplying this together, we would get 50 kilohertz. So we just use the same prefix used by the frequency deviation, and we just multiply 5 by 10, so we get 50 kilohertz as our peak frequency deviation. Let's have another example. So this time around, let's say this would be our number 1 example. Let's have a second example. in which we were given a deviation sensitivity of 35 megahertz per volt, and a peak modulating signal voltage of around 3.5 volts. So of course, the 35 megahertz per volt would be our K2 or K sub 2, and our 3.5 volts would be our peak modulating voltage. And from just like the first example, we just have to multiply them together. So we have 35 megahertz per volt. Multiply it with 3.5 volts. So the volts would just cancel out, and the unit would of course be megahertz. So 35 exponent 6 multiplied by 3.5 would be equal to 122.5 megahertz. It's 122.5 megahertz. So it's as easy as multiplying the two of them together. Now, the next thing that we have to determine is what we call our modulating index or modulation index. So it would be different from amplitude modulation, as we would be using our aforementioned frequency deviation, and this time around we would be using our modulating frequency. There are certain types of problems where the frequency deviation is already stated, and it's just as easy as dividing the frequency deviation with the modulating frequency. But there are times that in lieu of the frequency deviation, you would have to determine frequency deviation as the FM modulator deviation sensitivity, and modulating signal voltage or amplitude is the one given. So we will be using the previous problems as a way to determine frequency deviation. We could also directly put it in the formula. So instead of having f of d here, we could actually put the formula for frequency deviation sensitivity multiplied by the amplitude right here. So let's try answering the first problem first. So in this scenario, the frequency deviation is given together with the modulating frequency. So it's just as simple as having our m sub f. So we have our f of d and our f sub m. F of d is our frequency deviation. So don't mind the plus minus 12 kilohertz. This plus minus here means that the frequency deviation changes above 12 kilohertz and below 12 kilohertz from the frequency of the carrier. So it's just a matter of writing the 12 kilohertz here. Dividing it with 2.5 kilohertz, which is the modulating frequency or the frequency of our original signal or intelligent signal. As mentioned before, if we're trying to divide two values having the same prefix, in this case kilo, it is okay to divide them directly. But if you want to be sure, you can still put in the prefix on your calculator, as having two prefixes of different magnitudes can't be divided or multiplied directly, as they are, remember, they are representing different exponents of 10. So let's say we're going to do it directly. 12 exponent 3 for 12 kilohertz divided by 2.5 exponent 3 or 2.5 kilohertz, which will give us 4.8. So our answer here would be 4.8. So that would be our modulating index, or modulation index. Well, you could do it because they have both kilo. You can actually divide them directly. But the only reason we were able to do it is because they have both kilos here. If they have different prefixes, that would not have been possible, and you will get an incorrect answer. Let's look at the second problem here. This time around, the frequency deviation is not explicitly stated, but the deviation sensitivity and the amplitude of the modulating signal is given. So that means, using our previous formula for maximum frequency deviation, we could just multiply modulator's deviation sensitivity with the amplitude. But we have a modified formula here that allows us to do it directly. So we just put the K2Vm at the top and divide it with the frequency of the modulating signal. So that means our modulating signal would be equal to K2Vm. Remember, our K2Vm is our frequency deviation, and then divided by our frequency of the modulating signal. So K2 is 80 kilohertz per volt. Multiply it with the amplitude of 4.5. And then divide it by our frequency, which is 50 kilohertz. So it is actually very important that, especially in worded problems like this, you understand what the given is. It's not every time that the variables are stated explicitly, and you have to determine your plan of attack in solving these types of problems. So in this case, we have our 80 kilohertz multiplied by 4.5. That would give us 360 kilohertz. Divided by 50 kilohertz. And that would give us a frequency or a modulation index of 7.2. If you notice, I directly divided 360 with 50 as they are both kilo. Again, if they have different prefix, you're not allowed to do that. Now, with our modulating signal frequency deviation and the frequency of the modulating signal given, we're actually able to determine its approximate bandwidth. The bandwidth of FM actually has a couple of ways to be determined. You can use what we call the Carson's rule, or you could use our Bessel function table as a means to determine the actual bandwidth of the signal. So for this specific topic, we'll be focusing first on the determination of the bandwidth using Carson's rule. So let's now try to determine the bandwidth using what we call Carson's rule. So this is a good way of being able to easily approximate the bandwidth of an FM signal using its frequency or maximum frequency deviation and maximum modulating signal frequency. So we just add the two of them together and then double it or multiply it by 2. So let's use Carson's rule in order to determine the bandwidth for our previous problems in the modulating frequency, as we already have the necessary values in order to determine bandwidth. For this first one, we have a frequency deviation of 12 kilohertz and a modulating frequency of 2.5 kilohertz. So we just have to have our bandwidth is equal to 2 multiplied by the frequency deviation of 12 kilohertz added with our modulating frequency of 2.5. Now we could add these two directly, as again they have the same prefix. We can't do that if they are not having both kilo, both mega, or whatever prefix is written there. So 12 plus 2.5 is possible, again, because they have the same kilo as the prefix. Then we multiply it by 2, we get 29. Of course, we keep the prefix of kilohertz. Okay? So this would be its bandwidth according to Carson's rule. Let's now apply the same formula, Carson's rule, in order to determine the bandwidth for the second problem. So we have our FD max here, which we were able to determine as 360 kilohertz. Remember that in the second problem, the frequency deviation was not explicitly stated. So we had to calculate, and we were able to get it as 360 kilohertz. So we will have our, nope, not this one. We will have our bandwidth as equal to 2 multiplied by 360 kilohertz plus 50. Okay. So you can add this directly as they have both kilo. So 360 plus 50 would be 410 multiplied by 2. That would be 820 kilohertz. So that would be the approximate bandwidth according to Carson's rule. So we're done with determining frequency deviation, modulation index, and bandwidth for FM. Let's now try to finding the modulation index and frequency deviation for the phase modulation. As you will notice a difference with how they are calculated. Now, let's take a look at how we are able to determine frequency deviation and modulation index for phase modulation. So this would be a bit different, although we already had studied before that there are actually quite many similarities between FM and PM, but there are also distinct differences between them. First and foremost, the modulation index and phase modulation is actually the same. Technically, if you get the phase modulation or the change in phase in PM, that would also be its modulation index. And once you get the modulation index or phase modulation, that would be the time you will be able to get its frequency deviation. As we have mentioned before, a change in phase in PM also exhibits a change in frequency, and vice versa. Although we did not get a phase modulation or the phase deviation for FM. So for the modulation index, we just need to multiply the deviation sensitivity of the PM modulator multiplied with the peak modulating signal amplitude. In our previous discussion, this is what we do to get the frequency deviation. But for PM, this is the phase deviation, which is also our modulating index or modulation index. Once we get the modulation index or the phase modulation, which is denoted by K1 multiplied by Vm, we can actually multiply it by our modulating signal frequency, and then we will be able to get our frequency deviation. Let's take a look at these two examples in which the given would be able, from the given, we will be able to determine both of these two. So let's just move this a bit downward, our second example. So we have a PM modulator that has a sensitivity deviation of 2.5 radiations per volt, or rads, not radiation, or rads per volt, sorry. So if the modulating signal and frequency is 4 volts and 40 kilohertz respectively, we are to determine the PM modulation index and the frequency deviation. As stated, our PM modulation index is our also phase modulation, and it's as simple as multiplying our K1, which is the 2.5 radians per volt, multiplied by the modulating signal voltage, which is 4 volts. So with that, we multiply the two together, we will be able to get 2.5 multiplied by 4, which will be equal to 10 radians. So among the modulation index, this is actually the only one that has a unit. So the modulation index for AM and FM are unitless. But for PM, it would be radians or rads. Once we determine the modulation index for PM, then we will be able to get the frequency deviation. So the frequency deviation is actually the K1 Vm, which is this one already, multiplied by our signal frequency. So we already have the 2.5 times 4, so we have the 10 here. So it's just as simple as multiplying it by 40 by 40 kilohertz. So 10 times 40 would be 400 kilohertz, and that would be our frequency deviation. The formula for bandwidth stays the same. So if we are to get the bandwidth or approximate bandwidth, we can use Carson's rule, in which we just multiply 2 with the f sub m, or modulating signal frequency, and the deviation frequency. So there's no change in the formula here. And f sub m is 40 kilohertz. (40K) hertz here. Our frequency deviation would be the one that we got from the second computation, which is 400 kilohertz. So we just add these two together and multiply it by 2. So 40 plus 400. Again, they have the same prefix of kilo, so it is okay to add them together. But again, be warned that if they don't have the same prefix, you have to add it manually. Or you have to take into consideration their prefix before adding. In this case, 40 plus 400 would be 440 times 2. That would be 880. And we just keep the unit and prefix, which is in kilohertz. Right here. The second example is technically the same, only with different given. So we get our modulation index, also known as our phase modulation, denoted by delta theta here. So in this case, the K1 is 4 rads per volt. So 4. The modulating signal voltage is 3 volts. And that would give us 12 radians. Please be mindful of the units, as that is an important part of the answer. So 12 radians. Afterwards, we will be able to get the frequency deviation, which is the 12 radians that we got a while ago, multiplied by the signal frequency, which is 60 kilohertz. So 60 kilohertz multiplied by 12. So that would be 720 kilohertz. And then with the bandwidth, so we multiply the sum of our signal frequency, which is 60, and we add the frequency deviation to it. So 60 plus the one that we got a while ago, which is 720. So 60 plus 720 would be 780. Okay. And then multiply it by 2 would be 1560 kilohertz. Which is equal to 1.56 megahertz. So we just move these three together and we get the 1.56 megahertz. So that is how we are able to determine modulation index, frequency deviation, and bandwidth for PM signals. Up next, we would be looking into deviation ratio and percentage modulation for both FM and PM. Let us continue with determining percentage modulation and deviation ratio for both FM and PM. So as I mentioned, these two specific values are applicable for both FM and PM. As explained in our lecture discussion, percentage modulation will be the ratio of the actual frequency deviation over the maximum frequency deviation. So this just determines how much in percent is the frequency deviation being used compared to its maximum frequency deviation. While deviation ratio would be the ratio of our maximum deviation ratio over the maximum frequency of the modulating signal. So this just relates our deviation ratio with modulating signal in its maximum quantity or amplitude. So let's have an example first with getting the percentage modulation. So it's just as simple as dividing our frequency deviation or the actual frequency deviation multiplied by the maximum allowed deviation. In that case, in our given here for PM, we have a maximum allowed deviation of 12 kilohertz. That would be our maximum or frequency deviation max. And then an actual deviation of 7 kilohertz. So that would be our actual frequency deviation. So we just have to divide the two of them together and then multiply them with 100. So that would be 7, which is the actual frequency deviation, divided by 12, which is the maximum allowed frequency deviation. As they have both the same prefix of kilo, it would be okay, as mentioned, to multiply or to divide them directly before multiplying them with 100. So 7 divided by 12 times 100 would result in 58.33%. The unit of percent modulation is already found on its name and should be in percent. So we need to have the actual and the maximum frequency deviation on hand to be able to solve this. If we don't have an actual frequency deviation, we won't be able to get the percentage modulation for both FM and PM. Going into our deviation ratio, so we just have to compute our maximum deviation ratio and our maximum frequency for the modulating signal. If in some cases it is not explicitly stated that they are the maximum frequency deviation or maximum frequency for the modulating signal, we can assume from the problem that they are the ones that are given. The ones that needs to be said explicitly would be the actual deviation ratio, which is needed for percentage modulation. So we just need to divide our maximum frequency deviation with our maximum modulating signal frequency. So let's use this as part of our problems here for FM and PM. So let's try to use it here for our FM. Okay. In this case, our maximum frequency deviation was given at 12 kilohertz, and the maximum modulating frequency is 2.5, which is actually equivalent to our M sub F. And that is what you need to know with deviation ratio. For FM, deviation ratio and modulating signal or modulation index for FM are equal. Let's try. Remember that the modulation or the frequency deviation is 12 kilohertz divided by FM max, which is 2.5, which is basically the same one here. So we can be 100% sure that our deviation ratio is equal to 4.8 as well. That means for FM only, deviation ratio would be equal to modulating index. So if we are to get the deviation ratio for this one, well, we don't have to actually compute, as deviation ratio for FM is equal to modulation index for FM, which is 7.2. But for phase modulation, that would be a different case. So let's try using our deviation ratio formula here. Oops, not meant to do that. Oh, just this one little thing here, guys. Okay, apparently it's not allowing me to. Hey. Well, I give up. So you just have to remember that we need our maximum deviation ratio divided with our modulating signal frequency. So in this case, our frequency deviation is 400 kilohertz. So we are again trying to determine deviation ratio, which is equal to frequency deviation maximum and modulating signal frequency. In this case, frequency deviation is 400 kilohertz. Divided by the frequency of the modulating signal here. And that would be equal to 10. Which is actually also equal to our modulation index for PM. The only difference is that deviation ratio does not have a unit, but for modulation index of PM, it has a unit of radians. With that knowledge, you could actually surmise that this 12 here, or our deviation ratio, is actually equal to 12. or which is actually 720 kilohertz divided by 60, which is equal to 12. So we just have to remove the radians and we will be able to get the deviation ratio. So that is actually how easy it is to determine once you have your modulation index for both FM and PM. The deviation ratio, please remember, is just equal to our modulation index minus the unit. So deviation ratio is actually supposed to be unitless. The next part would allow us to determine the frequency domain of an FM signal given its modulation index. Remember that one of the primary differences of FM and PM over AM is that depending on the modulation index, we could have actually multiple sidebands. And those sidebands have varying amplitudes, but it is usually much larger compared to the carrier signal, which gives it a much more higher efficiency in transmission. So let's take a look at how we are able to determine the frequency domain of our FM and PM signal using what we call the Bessel function table. Okay, before we head out to the determination of the frequency spectrum using the Bessel function table, let's show your understanding of today's lesson given the past examples that we have for getting frequency deviation, modulation index, bandwidth, percent modulation, and deviation ratio. So, take a look at this exercise and upload it to where we usually upload it, depending on our class. Okay? And make sure that you put in your complete solutions and box your final answers. Okay, now let's go to our Bessel, the discussion of the frequency spectrum of FM, determination of the sidebands, and the Bessel function table. In order to determine and draw the frequency domain of our FM and PM signals, we would be needing a special table called a Bessel function table, which actually lists our modulation indexes here on the left side, and it is able to give the corresponding height or amplitude of the carrier together with the number and amplitude of the sideband pairs. So that means if we have a modulation index of 1, the carrier would have an amplitude of 0.77 or 77% of the power. Then it would have 3 pairs of sidebands, 3 in the upper and 3 in the lower. And this would be their corresponding height. Let's try and draw the frequency domain of this specific type of FM. So that means we would be needing our frequency domain. Let's write a ruler here. Let's draw a straight line here. This would be our x-axis, which would be relating to frequency. So the first thing that we have to do, so we were given that the modulation index is 1. From our table right here, the 0.77 actually relates to the carrier, which is 0.77. So that is the one that we're going to draw first. Just get a virtual ruler here. So it should be actually in the middle. So let's just write somewhere here. And we put in appropriate levels. So we at the bottom, we put in the frequency of the carrier. As it was not given, we just put in FC. Okay? And then at the top, we just put in 0.77. If the amplitude was given, we multiply it by 0.77 of the amplitude of the carrier, or the original carrier. So again, this part here is represented by this one. So we have a modulation index of 1. We draw the carrier first, put a vertical line corresponding to 0.77. Next, we put in our first set of sidebands. Now, it should be smaller, so it's up to you how you would be able to scale it compared to 0.77. So that will be around half. That really doesn't have to be exact. So this would be our first sets of sidebands having a height of 0.44. So we should not forget putting in the height here. But what about at the bottom? How far is the frequency of the first sideband from the carrier? So this is actually just equal to the frequency of the carrier plus the frequency deviation. Frequency of the carrier plus frequency of our deviation frequency. So that is for the first pair of the sidebands. Let's take a look. So we also have the next pair of sidebands from the Bessel function table, there's actually 3 possible sidebands. So the second one, so let's have our handy dandy ruler here. So it says here that it's supposed to be around 0.11 here. So just make the necessary adjustments for the estimation of the height or amplitude of the line. So this is 0.44, so that would be around 25%. So somewhere right here would be enough. And don't forget to put another one on the lower part. So this would be 0.11. This would be 0.11 as well. So that would be our height label. And this would be, or the frequency would be the carrier frequency plus twice the frequency deviation. Let's have a sample later on that has a given carrier frequency and frequency deviation. Okay, so that will be able to properly complete the label as opposed to doing it using the variables. So let's look at the last sideband. The last sideband is 0.02. That is actually quite small. So it's almost very short here. Okay. And another one here. That'll be enough. And of course, as always, let's put in the label 0.02. 0.02 in here as well. And this would be around FC, or carrier frequency, plus 3 times the frequency deviation. So let me just correct what I've written here. As the ones here should be in subtraction. Unfortunately, I put in addition. So FC minus 2FD, because this is in the lower sidebands, or the lower part of the sideband. So this is supposed to be minus as well. So this would now be our completed FM frequency spectrum with corresponding labels and amplitudes. Let's have another example. But this time around, let's give a proper givens for the following. So let's say our M, or modulation index, was equal to 1.5. What if the modulation index you got is nowhere in the modulation index? You just go ahead and round it off to the nearest modulation index and proceed from there. Although there is a method of actually determining the exact sideband pairs and their amplitude given a specific modulation index, unfortunately, that is beyond the scope of our discussion. So to simplify things, you just round it off to the nearest modulation index, then proceed from there. Let's say we have a carrier frequency of 100 kilohertz and a frequency deviation, or maximum frequency deviation, of 3 kilohertz. And we are tasked to actually create or show the frequency spectrum of this signal complete with its proper labels. So this time around, we'll be able to put in frequencies for the Bessel function table, or from the Bessel function table. Let's start, of course, with the horizontal line, or our x-axis, which would show us the range of frequencies we need. Okay. And as always, we use a vertical line to represent our carrier frequency. So in this case, the carrier frequency for 1.5 written here. So this is 1.5. So the carrier is 0.51. So we start with 0.51 here. So it's up to you how to do that estimate. So let's say this is 0.51. So we don't forget the label. And because the frequency was given, so this would be 100 kilohertz. There we go. Then we proceed to this first set of sidebands. So this time it will be 0.56, a bit higher than the carrier. Almost equal. We just put that a bit above 0.51. Just to show that, properly show that 0.56 would be higher than 0.51. So let's put in 0.56 here. And another 0.56 here. So how about the frequency? So the frequency here would just be 100 kilohertz plus and minus 3 kilohertz. So that would be 103 here, which is 100 plus 3. So it's plus because it's in the upper sidebands. And then from the one lower would be 97. That would be 100 minus 3. Then we proceed with the next sidebands. So we're just going to finish it up to the second sideband, although it actually has 4 sidebands. I'm just going to show what we do, then you can actually just continue it later on. So the second pair of sidebands would be 0.23, or around half of our 0.56. So let's just put it around half here. You don't have to be exact, as long as you're scaling it to the values here. So this would be 0.23, and this would be 0.23. Okay, and then we add another 3 kilohertz here because of the frequency deviation. So the amount you add, of course, is based on the frequency deviation. Then we subtract 3 from here. So from 97, this becomes 94. Then you just follow the steps for our third set of sidebands, which is 0.06 and 0.01. Then you put in the proper frequencies. So remember to follow the number of pairs of sidebands here, which is equal to 4. Next up, let's take a look at how we determine some of the factors in computing for the quality factor and shape factor, which are important aspects of receivers, which actually denotes our selectivity, as we had discussed from our previous discussion. Okay, so let's take a look into looking or computing shape factor and Q factor, 2 of the ways to be able to determine the selectivity of a given receiver, regardless of its type of modulation, maybe it AM, FM, or PM. The first one, as we've discussed in the lecture, is determining the shape factor. So the shape factor is actually determined by the bandwidth in the negative 60 decibel over the bandwidth of the negative 6 dB, which technically shows us the ratio of the bandwidth where the signal is sufficiently attenuated over the bandwidth of the signal where the highest amount of power or the least amount of attenuation is located. The bandwidth could actually be gathered by subtracting the 2 frequencies for the negative 60 dB mark and the negative 6 dB mark, which is represented here by F4 minus F3 and F2 minus F1. Now, Fortunately for us, the bandwidth is actually given as its absolute function. So it's just a matter of dividing the 60 dB with the 6 dB mark. Okay? It's almost always that this is greater than 1, okay, and never lesser than 1. So if you get an answer lesser than 1, either the question is incorrect or you were able to reverse it in putting in the values. You put the negative 6 dB bandwidth at the top and the negative 60 dB at the bottom. So, as mentioned, our shape factor would just be equal to the negative 6 dB, which is 8 kilohertz. 8 kilohertz divided by the 3 kilohertz. As mentioned several times already, because the two values are in kilo, that means we could actually divide it as is, 8 divided by 3, and then we get around 2.67. Please remember that the shape factor is unitless. As we mentioned through the lecture, the closer it is to 1, the better the shape factor is. Let's try getting the shape factor for the second example, and let's try to compare it from the first example. So we have here the negative 60 dB bandwidth of 500 kilohertz and a negative 6 dB bandwidth of 100 kilohertz. So you could just directly divide 500 kilohertz over 100 kilohertz. So 500 divided by 100, we can directly divide this as they both have kilo. That would be equal to 5, or a shape factor of 5. That would mean that our second receiver has a worse selectivity compared to the first example. As the closer it is to 1, the better it is. Now let's take a look at how we determine quality factor. The quality factor is just a ratio of the resonant frequency in a tuned circuit or the operating frequency of the signal divided by its bandwidth. So let's say we have an AM broadcast system here, and we are to determine its quality factor. So the resonant frequency given from this one, okay? So this is at the frequency. This is the operating frequency right here. So that it isn't stated explicitly that this is the resonant frequency, but once the operating frequency of the signal is given, that would automatically be the resonant frequency. So our FR would be 540 kilohertz. And it was stated explicitly here that the bandwidth is 10K. And just like with our other computations, because they are both, or they both have a prefix of kilo, dividing them directly is possible. And that means we would be able to get a quality factor of 54. Quality factor, just like our shape factor, is unitless, as the hertz would cancel out. This just tells us that our bandwidth is around 54 times smaller than the frequency that we're occupying. Let's take a look at the next example. So the resonant frequency here is stated explicitly as 150 megahertz. And a bandwidth was given as 50 megahertz. Now, getting the Q point, it's just a matter of dividing the two. Do you think we could divide them directly? Yes, we can, as they both have the same prefix as mega. If they have different prefixes, then we need to compute it with the prefix on, or with the exponents on, in the exponential notation. So dividing them both would give us a value of 3. So 3 is actually not a good quality factor. It really depends on the application, but that means that it actually occupies quite a lot compared to its resonant frequency. And there is a possibility that it will be occupying or interfering with other signals close to it. Now, I'll be giving you some exercise examples so as for you to be able to check or test your understanding for today's discussion. And there we have it. We're able to finish our discussion for today. As such, I'll be giving you the second part of the exercise, which allows us to check your understanding of first creating the frequency spectrum of FM and PM using the Bessel function table. Make sure that when you do this, you put in the complete labels, the same way that we did with the previous examples. And then we'll be able to determine or check your understanding of the shape factor and quality factor of receiver circuits that we have just finished a while ago. As always, if you have any questions or clarifications, kindly leave it at the comments or kindly comment me through my email. Thank you very much and have a great day.